Hello everyone. In this session, we will discuss about fluid kinematics. Now coming to overview of this session, first I will explain introduction to fluid kinematics. Then we will see two approaches of fluid kinematics. Then we will see classification of fluid flow. Then discharge. After that, continuity equation. Now coming to introduction about fluid kinematics. What is fluid kinematics? Fluid kinematics is a branch of science which deals with the study of motion. In fluid dynamics, the fluid kinematics is the study of how fluid flow and how to describe fluid motion. Kinematics is the geometry of motion. Therefore, the kinematics of fluid is that branch of fluid mechanics which describes the fluid motion. There are two fundamental approaches to describe the fluid motion are Langrangian method and Eulerian method. In Langrangian method, it requires the individual particle behavior to describe a fluid flow. We follow individual fluid particle behavior to describe motion in Langrangian description. In Eulerian approach, we define a control volume through which fluid flows in and out. The Langrangian method of describing motion is much more difficult for the fluids because we need the individual particle behavior to describe motion. In case of Eulerian method, fluid flow is described by defining a finite volume called a flow domain or a control volume. Instead of tracking individual fluid particles, we define fluid variables as a function of space and time within a control volume. In Eulerian approach, no need of individual particle tracking. We will consider fluid variables as a function of space and time within a control volume. Therefore, Eulerian description of fluid motion method is more commonly used to describe fluid flow. Therefore, Eulerian method or Eulerian method is most convenient method to describe the flow field. Now we will see the classification of fluid flow or types of fluid flow. Under that, there are 6 types. There are 6 classifications: steady and unsteady flows, uniform and non-uniform flows, laminar and turbulent flows, compressible and incompressible flows, then rotational and irrotational flows, and 1, 2 and 3 dimensional flows. Now we will discuss one by one. First one, steady and unsteady flows. Steady flow is defined as that type of flow in which the fluid characteristics like pressure, velocity, density at a point do not change with the time. That means the hydrodynamic parameters at a point will not change with respect to time. Mathematically we can write, if you take a properties of velocity, pressure, density with respect to time, it is not changing. That is, dou v by dou t is equal to 0. Dou P by dou T is equal to 0. Dou rho by dou T is equal to 0. Velocity, pressure, density with respect to time is not changing. Now coming to unsteady flow, in which the hydrodynamic properties at a point changes with respect to time. The properties like velocity, pressure, density, etc. with respect to time changes. Such type of flows comes under unsteady flow. That means change of velocity with respect to time is not equal to 0 because velocity is changing with respect to time. That is why dou V by dou T is not equal to 0. There is a change in pressure with respect to time. Dou P by dou T is not equal to 0. Dou rho by dou T is not equal to 0. This means velocity, pressure, density, all properties with respect to time changes in a unsteady flow. Now coming to uniform and non-uniform flows. When a velocity and other hydrodynamic parameters at any instant of time do not change from point to point in a flow field, the flow is said to be uniform. In unsteady and unsteady flow, we will explain the flow based on time. Here, uniform and non-uniform flows will be explained with the help of space. Uniform flow is defined as the type of flow in which velocity at any given time does not change with respect to space. This word is very important. Does not change with respect to space. Here with respect to time we will explain. That is why dou V by dou S equal to 0. S is the space coordinate, that is the length of the flow in direction of S. Dou V is the change of velocity. Now coming to non-uniform flow. Non-uniform flow is that type of flow in which the velocity at any given time changes with respect to space. Mathematically we can write dou V by dou S is not equal to 0. That means velocity with respect to space is changing, that is why this value is not equal to 0. Now coming to laminar and turbulent flows. A laminar flow is characterized by a smooth flow of one layer of fluid over the adjacent layer. The fluid particles move in well-defined path or streamlines and keep the same path at successive cross-section of the passage. That means in a laminar flow, all fluid particles will flow in well-defined path. That means in a streamline. That streamlines are straight and parallel to each other. In turbulent flow, the fluid particles will flow in a zigzag manner. There is no streamline in a turbulent flow. Turbulent flow in which the fluid particles move in a zigzag way. Due to the movement of the particles in a zigzag way, the eddies formation takes place, which are responsible for high energy loss. The Reynolds number will define the flow type, whether it is laminar or turbulent. The non-dimensional number, that is Reynolds number, will signifies whether the given flow is laminar or turbulent. Reynolds number will give the clear picture about the type of flow.
If the Reynolds number is less than 2000,
then such a type of flow is called laminar flow. If the Reynolds number is in the range of 2000 to 4000, then flow is said to be transition flow. If the Reynolds number is greater than 4000, then the flow is said to be turbulent. So significance of Reynolds number, which will give the idea about whether the flow is laminar or turbulent. Now coming to compressible and incompressible flows. Compressible flow is that type of flow in which density of the fluid changes from point to point. Density is not constant for the fluid. That is, density is not constant in a compressible flow. Density is keep on changing from one point to point. So incompressible flow is that type of flow in which density is constant for the fluid flow. Liquids are generally incompressible while gases are compressible. That means for the liquids the density remains constant, while for the gases density is not constant, that is, which can be compressible. Now coming to rotational and irrotational flow. Rotational flow is that type of flow in which the fluid particles rotate about their own axis. Rotational flow in which the fluid particles rotate about their own axis. Such fluid flow is called rotational flow. Then what about irrotational flow? The flow in which the fluid particles do not rotate about their own axis is called irrotational flow. Now coming to 1, 2 and 3 dimensional flows. 1D, 2D and 3 dimensional flows. One dimensional flow is that type of flow in which the flow parameter such as velocity is a function of time and one space coordinate only. That means this velocity is a function of only one coordinate, maybe x, maybe y or z. If you take x, then in velocity in y direction and z direction becomes 0. That type of flow comes under one dimensional flow. If depends on two coordinates x and y, then it is a two dimensional. If depends on three coordinates, then it is a three dimensional. One dimensional means this velocity is a function of only one coordinate only. Then two dimensional flow, the flow in which the parameter such as velocity is a function of time and contains two space coordinates. 2 means x or y, x comma y or y comma z or x comma z, any two space coordinates. That is written here. V is a function of x comma y comma t. T is time, x and y are space coordinates. For a steady two-dimensional flow, the velocity is a function of two space coordinates only, and the variation of velocity in third direction is 0. Here it is, velocity is only depends on one space coordinate, remaining two coordinates velocity is 0. You can observe here v and w values are 0. V is the velocity in y direction, w is the velocity in z direction. Similarly here velocity in z direction is 0 because it is a two-dimensional flow. We considered x and y. Now coming to three-dimensional flow, the flow in which the parameter such as velocity is a function of time and contains three space coordinates x, y and z. That means velocity is a function of x, y and z space coordinates, u value, v value and w value. U is the velocity in x direction, v is the velocity in y direction, w is the velocity in z direction. Such type of flow comes under three-dimensional flow. All three space coordinates velocity are existing in three-dimensional flow. Now coming to rate of flow or discharge, it is also called volumetric flow rate. It is defined as the quantity of fluid flowing per second through a cross section area. It is a rate of flow of volume. It is a rate of flow of volume. Flow of a volume of the fluid per unit time. Flow of volume of the fluid per unit time. That is called volumetric flow rate. The SI standard unit for this is meter cube per second. The formula is given by Q is equal to, Q is the notation for the discharge or rate of flow or volumetric discharge, volumetric flow rate. Q is equal to area into velocity. Finally, SI unit becomes meter cube per second. Area meter square and velocity meter per second. Area into velocity will give you Q, that is volumetric flow rate. Now coming to continuity equation or conservation of mass. Here we have to consider fluid flow through a pipe which has a two cross section, 1,1 and 2,2. Density, cross sectional area and velocity at inlet is named as ρ1, A1 and V1, and density and cross sectional area and velocity at cross section 2 is named as ρ2, A2 and V2. According to the conservation of mass principle, whatever the mass flow rate into the system 1,1 is same as at cross section 2,2. That they have equated here. The rate of flow at section 1,1, that is mass flow rate through section 1,1, that is ρ1 into A1 into V1. ρAV is the formula for mass flow rate, and rate of cross section at 2,2, nothing but ρAV is the formula, but at section 2,2, what is the density? ρ2. What is the cross sectional area? A2. And what is the velocity? That is V2. So ρAV is the formula for mass flow rate. Whatever the mass entering into 1,1, same mass is leaving at 2,2 according to the conservation of mass principle. So you can equate both values are equal. That is why rate of flow at section 1,1 is equal to rate of flow at section 2,2. ρ1 A1 V1 is equal to ρ2 A2 V2. For a fluid, we will consider density is not changing, that is incompressible fluid. ρ1 again equal to ρ2, ρ get cancelled, then finally we will get A1 V1 equal to A2 V2. The above equation is called continuity equation. Generally we will use A1 V1 equal to A2 V2 for the fluids, because generally all fluids are incompressible in nature. Density ρ1 at section 1,1 and ρ2 at section 2,2 are one and the same, ρ1 equal to ρ2, which get cancelled. Remaining is A1 V1 equal to A2 V2. Discharge equation is area into velocity. Discharge equation, volumetric flow rate, that is a volumetric flow rate, area into velocity. What is mass flow rate? That is rho into area into velocity. Rho into Q is nothing but mass flow rate. Density into discharge will give you mass flow rate. Please remember, here in a continuity equation derivation we need mass flow rate. We are deriving the equation for conservation of mass or fluid flow through a pipe, continuity equation. For that we need mass flow rate equation, that is ρAV entering at section 1,1, that is ρ1 A1 V1. At section 2,2 it is the exit of mass flow rate, ρ2 A2 into V2. Just equate these two, because according to the conservation of mass principle, whatever the mass flow rate entering into section 1,1, same mass is leaving at section 2,2. So if you equate, you will get A1 V1 equal to A2 V2. With this, I am concluding this session. The following references are used for the preparation of these slides. Thank you.